Ladies and gentlemen, esteemed judges and honored guests, welcome to the joint Lufthansa Group and Google Research presentation for the prestigious 2025 Franz Edelman Award. We are thrilled to have you here today to witness the innovative solutions and groundbreaking work that our collaboration has accomplished. And we sincerely hope that you find our presentation both inspiring and insightful. My name is Christian. I'm leading the Department for Digital Operations Optimization at Lufthansa Group. And today, I'm joined by Toby Davies, Staff Software Engineer from Google Research. The overall impact of our project is truly remarkable. We have achieved estimated savings of $40 million and a reduction of 12,000 tons of CO2 since the introduction of the first tool back in 2021. And this is not just a number. It's a real step towards our ambitious goals, halving net emissions by 2030 and achieving climate neutrality by 2050. We automated one process from taking the full duration of an ops controller's 8-hour shift to just 3 minutes using one of our tools, freeing up valuable resources for critical decision-making and increasing employee satisfaction by relieving them from routine tasks. Also, we ease the experience of our customers by handling their journeys in a more efficient and proactive way, but I will get back to that in a few minutes. The Lufthansa Group is the fourth largest aviation company with more than 100,000 employees composed of several airlines including Lufthansa, Swiss International Airlines, Austrian Airlines, Brussels, Eurowings and our newest member ITA, formerly known as Alitalia. Together we provide seamless connectivity and premium service across Europe and beyond with a fleet of more than 800 short and long-haul aircraft via a multi-hub, multi-airline and multi-brand system. Collectively, these brands delivered remarkable commercial results in 2024, operating almost 1 million flights with more than 130 million passengers, showcasing resilience and excellence in an ever-evolving industry. Our commitment to sustainability remains unwavering. We are dedicated to reducing our environmental footprint to achieve carbon neutrality by 2050. Our efforts include investing in modern and fuel-efficient aircraft, advancing sustainable aviation fuels, and optimizing our operations to minimize waste. We believe that sustainable growth is not just a goal, but a responsibility. And we are proud to lead the way in making air travel greener and more efficient. Welcome to our journey. And we are approaching now the same destination where also our journey with our project started about 6 years ago at the hub of our subsidiary Swiss in Zurich. In the following minutes, I want to give you some background on how our airlines and mostly every airline in the world steers its operation before we present our solution to make this even better. Operations control centers in airlines are crucial for monitoring and steering flights. They work to improve operational efficiency by ensuring timely departures and arrivals. Mostly important, they are there to resolve regularly occurring disruptions, also called irregularities, and provide solutions for our customers in real time. Recovering from a disruption is a complex process that potentially requires aircraft to be reassigned, maintenance to be rescheduled, crew to be rerouted, and passengers to be rebooked. So even though you might feel alone as a passenger sometimes, someone in operations control is always looking at your journey. The traditional way to manage complexity is by dividing the problem and addressing each part with expertise. By breaking down a complex issue into smaller segments, teams can focus on individual aspects without feeling overwhelmed. And the daily operations of 10 airlines at the Lufthansa Group is complex by coordinating hundreds of aircrafts with more than 2,700 flights, more than 6,000 active crew members, and more than 300,000 passengers per day. This needs continuous communication and collaboration among team members to maintain a cohesive approach and ensure that all parts always align seamlessly. Let me explain it a little bit further with an example of Alex-64 from Zurich to Miami. A technical malfunction was identified in the pre-flight check by the pilots, and they informed the operations control center accordingly. They now have to come up with an alternative solution to mitigate the impact of this disruption. One important department in operations control is the hub control center. They ensure smooth operation by managing passenger flows, coordinating aircraft turnarounds, and collaborating with partners. The network operations control centers, or also called operations control centers, are essential for monitoring and managing aircraft movements. They ensure timely departures and arrivals by coordinating flight schedules. In our case, it's on them to come up with an alternative solution like delaying or canceling the flight to handle the situation. Crew control in an airline ensures compliance with duty regulations, manages crew qualifications, and optimizes crew assignments. For LX64, a delay is possible that would exceed the crew duty time, and it needs to be evaluated whether a reserve crew is available and should be activated, which is also a favorable solution from network operations control perspective. But before we can make a final decision, the impact on the passengers need to be considered. Due to the delay, some passengers already missed their onboard connection. Therefore, the passenger care center starts rebooking passengers not only on the outbound flight, but also on the inbound flight that needs to be delayed accordingly. So you can see that the work on operations control is characterized by sequential decision-making and by splitting problems across the different departments. Each of them is equipped with legacy systems and sometimes even with effective optimization solutions. But this is the process for just one flight, and already many colleagues are involved. And we are far from having an integrated decision, which is not necessarily close to being a good or optimal solution. It's just a feasible one. We spent more than $900 million last year on irregularity costs, such as compensations and hotel accommodations. Optimizing these costs holistically will directly increase our profit and will improve the experience of our passengers during disruptions. And this is not a new challenge. It was already significant in 2018. Therefore, we embarked on a transformative journey. Our vision emphasized the necessity for an AI-enhanced, unified, and integrated operations steering decision support suite, or as we call it, OPSD, focusing to improve the typical operations KPIs like punctuality or regularity. And this is still true. But COVID and the restart of air traffic showed us that there are even bigger targets that make such an innovative solution not a nice to have, but rather a necessity to provide efficient and profitable service. We want to enhance resource efficiency through optimized and database decisions, elevate customer satisfaction by proactive decision-making, and reducing staff dependency and intensity while automating processes. Google's commitment to solving complex problems and their long-term vision of achieving fully holistic decision-making makes them an integral part of this ambitious and industry-unique approach. OPSD is built as an additional cloud layer in our today's IT architecture, augmenting existing legacy systems rather than replacing them. By this, we create a degree of freedom by making it communicate with existing tools and data in a state-of-the-art cloud infrastructure. From the beginning, we aimed for scaling or transferring this solution across all of our airlines while standardizing in terms of systems, data models, or processes. Therefore, we introduced 3 layers in our cloud platform. The first layer is our buffer to make it adaptive enough to onboard different systems. So the second layer is a digital representation of our operations, a digital twin based on a newly introduced data model for all airlines. Everything that we build up in that is built on a one code base. This layer also contains all the necessary business logic that is developed based on the input from our staff. With this, we are able to compile feasible solutions for different optimization scenarios, bringing together the different perspectives in operations control. Lastly, we hand over our prepared scenario data and a target function to the solver developed by our dear colleagues from Google and let them do their magic. The result is then fed back to our legacy systems and can be reviewed by the user and executed in the same way like he or she would have compiled an own solution manually. Our architecture is built in a microservice environment across the mentioned layers on our platform to make it as efficient and reusable as possible. It's accompanied by our own data science environment to also allow to use AI and GenAI models for different tools. The user output thereby is highly adaptable to the needs of the user, whether we implement our solution in an existing workflow, just provide generated data, or have our own standalone web user interfaces. We do all this groundwork on data to leverage the core of our partnership with Google Research, the expertise and technology in the applied OR team of Google Research. And Toby will now give you a deep dive into our approach of solving these challenges.
Hi, I'm Toby. I'm a software engineer working on Google's Applied Operations Research team. Christian's told you a little about the business and data preparation parts of this problem, which were handled by the Lufthansa group themselves. I'm going to talk a little bit about how the applied operations research team modeled the underlying optimization problems and the operations research techniques that we used to tackle them. I'm not going to go particularly deep into any of these details, but I do hope to give you an overview of the optimization problems and the techniques that we used and how they fit together to form a cohesive decision support tool. So the first thing that we noticed is that ops controllers are really resolving disruptions in two parts. They first mitigate the immediate problem, which requires a good enough plan found quickly, and then they re-optimize after the immediate impact has been resolved. There's no point spending hours deciding the best possible plan for the rest of the day if an aircraft needs unexpected maintenance and its next flight is scheduled in half an hour. If you have another aircraft available, if you take more than a few minutes to decide what to do, the best plan using that aircraft and departing on time is simply no longer possible because your decision was too slow. On the other hand, once that schedule is stable again, it's absolutely possible and worth it to spend an hour computing the best possible aircraft to assign so that you use 1% less fuel over the next few days. Different optimization techniques make sense in these two cases, so we handle them separately. I'm going to talk about the reoptimization problem first for a few reasons. Firstly, humans are particularly bad at it. Secondly, it's a lot simpler to implement and to demonstrate the impact. And thirdly, we launched it first, and I think this story is better told in order. So the core of the reoptimization problem is the tail assignment. That is how we assign aircraft, which are identified by numbers painted on their tails, to flights. Different aircraft have different costs for operating different flights. In this diagram, the arrows are flights connecting different airports with time on the y-axis increasing as we go down. An initial optimized tail assignment is generated months in advance by a separate system. But a months-old system simply can't take operational realities into account. Sometimes aircraft have to be swapped, for example, due to unplanned maintenance. These changes can mean the original plan is no longer possible because aircraft aren't where they're supposed to be. There are many things affecting the assignment costs, but one of the more significant ones is fuel efficiency. And the difference between the most and least efficient fuel-efficient aircraft of the same type can be as much as 10%. And since we have a much better prediction of aircraft fuel efficiency today than we did a month ago, we can still optimize with no disruptions. People are not great at finding optimal tail assignments. I remember in the very early days of this project, we collected some example problems from the ops controllers in order to test the solver, that it was producing solutions that were feasible and it was computing the objective correctly. Our colleagues at Swiss used their decades of experience to generate a tiny problem and optimal solution with, I think it was 4 aircraft and somewhere between 6 and 10 flights. When the solver suggested changes, we spent days looking for a bug before we realized that the solver had actually found a better solution than the experts on this tiny problem. With OR techniques, this optimization can be solved fairly straightforwardly using a multi-commodity flow MIP model plus some constraints on aircraft maintenance. But obviously, that can't be all there is to this problem. So far, I've only talked about aircraft, which is nothing like the multi-department holistic optimization that Tristan talked about and is the whole reason for this project. So unfortunately, or perhaps fortunately for our story, there is a complication. Aircraft don't fly themselves. They need a crew, and those crew need to be qualified for the specific type of aircraft they're flying. For example, if we were trying to crew this schedule, there might not be enough time for the red crew to make this connection without the risk of delaying their departing flight. In this case, either we can force those 2 flights to be on the same aircraft so that the crew don't have to waste time walking between different aircraft, or we can choose a different crew. Traditionally, when tail assignments are produced months in advance, crew are assigned afterwards in that sequential style. So crew considerations are largely ignored when generating tail assignments. But this doesn't work if we want to change tail assignments only a few hours in advance. Crew might already be partway through a multi-day trip and need to come home at a certain time, or a specific crew might be rostered, that are rostered today might be close to their maximum allowed flight hours they can fly this month. Or we might not want to call a crew at 1 a.m. to tell them that they're now starting at 4 a.m. instead of 6. Hopefully they're asleep. So we have to take crew into consideration if we want to reassign aircraft so close to takeoff. Unfortunately, crew rules fill whole books. And to make it worse, these are different books for each airline, even within the Lufthansa group. We can simplify if we don't change the type of aircraft for any flight, and we force all tight connections to stay on the same aircraft, then an existing assignment will remain valid. And OPSD allows ops controllers to use this simplification and find optimal assignments under those restrictions very quickly. But these restrictions reduce the opportunities for optimization. The biggest differences in operating costs are between aircraft of different types, and these require differently qualified crew. So to handle this, we defined a black box rules API. This allows Lufthansa to write complex checking code in their programming language of choice, compile it into a WebAssembly library that can safely be run on Google servers, allowing low latency, high frequency communication. This API is essential for the transferability of our approach to the multiple airlines in the Lufthansa group, and potentially beyond. The core of this API is an incremental check. Can I add a specific next leg to a crew's itinerary? Then a depth-first search can use this to generate a set of possible crew trips, and a MIP is used to select a set of crew trips that fill the roles needed on each flight, given a tail assignment. Generating all the trips would generate far too many options to consider, so we only consider changing a subset of crew assignments that are close to the first-in feasibility in the crew plan. Then we loop and keep pushing that first-in feasibility back until it's past the end of a planning window, typically a few days in the future. This isn't guaranteed to find a plan, but it will find anything reasonably close to the original, which includes any plan that the manual process would have found. So, how do we get these components to work together? It's all well and good to be able to assign aircraft and then assign crew, but we really want to do these things together, otherwise we're just doing sequential planning again. To do this, we use a decomposition technique called logic-based Bender's decomposition. We generate a tail assignment and try to crew it. If we fail, we add a constraint to the tail model to generate a different assignment. Unfortunately, the flexibility of our crew rules API means that we have less structure to exploit in generating powerful cuts, which means that adding crew to a problem can mean it takes far longer to find any solution at all. We'd like to have the best of both worlds, something that can quickly find good solutions, like we did with a simple restriction, but can still find aircraft type changes where they have big savings. To do this, we add those overly conservative constraints to the solver, and then gradually relax them as we find solutions, or prove that we won't find any given these extra constraints. This allows the solver to focus on making aircraft assignment changes that are less likely to be incompatible with the existing crew plan, which means it's more likely to find something feasible. So in these diagrams, flights are boxes, and each row is an aircraft. The first two rows are the same type of aircraft. On the left, we have the original tail assignment, and on the right are two different potential schedules. One metric that we use to add an extra constraint to the solver is the number of flights with different aircraft types. So here, the first change has 2 flights which have changed their aircraft type, and the second has only 1. So by adding a constraint that limits the number of type changes to 1, the tail solver can only find that smaller change, which is more likely to be crewable. That was our approach to reoptimization. So far, we've managed to completely ignore disruptions and passengers. So how do we handle those? Let's take a step back. What is the recovery problem? So disruptions or irregular operations can be caused by many things, many outside of the airline's control. Crew can be sick or late to work. Weather can make some runways unsafe or necessitate de-icing before takeoff. Airspace or taxiways might be congested, so the airport has to delay some flights. And maintenance checks might ground an aircraft that we were planning to use at short notice. The solver itself doesn't really care about the disruptions themselves. Instead, the impact of all of these are compiled into a snapshot sort of state-of-the-world data structure generated by Lufthansa's code, which is then sent to the solver. This details where aircraft crew and passengers are, where they're expected to be in the future, and crucially, how expensive it is if we can't get them there on time. The solver can suggest a number of types of change that the ops controller to review and implement. Tail changes and crew planning are exactly the same type of suggestions made by the reoptimization solver. But now we also have the option to cancel or delay flights, or rebook passengers, or send buses to get them to the next flight quicker. These repair options are traditionally handled by different departments. But to identify what a good plan is, it is important to consider these repair options jointly. Passengers are the airline's major revenue source, and delayed or cancelled flights lead to compensation and, of course, poor customer satisfaction and lower future spend from those customers. How bad it is to cancel a flight depends on how easy it is to reroute those passengers. If you or a partner airline have 10 flights a day from Geneva to Zurich, cancelling one probably won't inconvenience travelers as much as cancelling a once-a-day flight from Zurich to New York. And before the OpsD project, ops controllers used heuristics like this to prioritize different options for repair. However, if a large number of passengers on a specific Geneva to Zurich flight are going on to New York, canceling or even delaying that Geneva flight might be far more expensive than the ops controller initially thought. And this is the kind of complexity that humans just can't handle. Swiss flies tens of thousands of passengers on hundreds of flights per day. Even if we wanted to consider a handful of different possible delays per flight, a simple mixed integer programming model combining aircraft and passenger recovery over a single day horizon would easily require 100 million variables. So we knew that to find a reasonable solution to a problem at this scale with a target runtime of under 5 minutes, we would need to decompose the problem and take advantage of the expertise in the operations controllers. So when we started designing this solver, we took inspiration from how the existing operations departments work. Mostly they work independently, but with some key communication to agree on a few key details. This inspired us to consider a simple decomposition, where subsolvers play essentially the same roles as the operations control departments, allowing us to take advantage of institutional knowledge from within the departments to implement heuristics. With this decomposition, we were confident we'd be able to at least emulate the manual sequential approach and get a reasonable solution quickly and use this as a starting point to improve. So to formalize what subsolvers need to agree on, we define a concept we call flight candidates. These capture the things that need to be agreed upon for each flight. When they're arriving and departing, what type of aircraft is assigned, and if there's a tight crew connection, what the previous flight on the same aircraft was. And there is, of course, the implicit option of canceling the flight. So we heuristically generate some candidates for the flights based on options the ops controllers set before we start trying to repair. Bringing this together a little bit, main idea is if all the subsolvers agree on which candidate is used for each flight, then they can optimize independently within their own domains. And to get the subsolvers to agree on what different candidates are chosen, we have a component we call the Reoptimizer because it optimizes irregular operations. The Reoptimizer guides subsolvers towards consensus by varying the cost of choosing various candidates. Subsolvers then choose a low-cost subset, subject to the constraints and additional costs that they are responsible for. The Reoptimizer has a bunch of different techniques that it uses to set these costs, and these can be mixed and matched. I won't talk about any of the subsolvers in detail, as I could easily talk for 20 minutes on each of them. And the beauty of our decomposition, though, is that it places very few restrictions on subsolver implementations. So all of them themselves are actually portfolios of different techniques, including fast heuristics, mixed integer programming models, and in some cases, decompositions themselves. You may note that we've combined a few departments into just aircraft, but it's still a fairly straightforward mapping from operations departments to subsolvers. So our first cost-setting approach is heavily inspired by the manual process. We estimate the cost of delaying and canceling flights by just assuming that passengers can't be rerouted. And then we choose the best flights for the aircraft subsolver, and we set the cost of any candidate that isn't chosen to infinity and pass it on to the next solver. If any solver cancels any flights, we set its cost to infinity and jump back to the start and keep going until we find a fixed point. One core part of the Reoptimizer is a integer program that chooses the best solution generated by each subsolver, subject to constraints that they agree with one another on what flight candidates are chosen. By solving the relaxation of this IP, we can get candidate costs from the dual solution, which we can send to the subsolvers. We can combine this with the sequential heuristic by picking one to go first, taking its duals, setting the cost to infinity for the next subsolver, and doing exactly the same process, but starting from not a pessimistic estimate, but the duals from the column generation. Finally, we also define some large neighborhood search neighborhoods, where we block certain types of candidate, again, by setting their cost to infinity. Some disruptions call for delays, others for using reserve aircraft, still more for changing the type. By forcing subsolvers to consider only a few types of changes at a time, we can reduce the computational effort that it requires to converge to a solution. This is similar to how ops controllers think about problems. If we can find solutions of similar quality to what would have been found manually, a good feasible solution really helps improve the convergence rate of column generation. Now I've explained a bit about how this solver works under the hood. I'm going to hand back to Christian to tell you a bit about how the tool has impacted operations at Swiss and the larger Lufthansa group.
The following section should be handled by our Vice President of Innovation in Tech Factory, but he unfortunately had an urgent medical issue and needed to fly back to Europe, so he cannot be with us today. But I will take over his part. Every single flight is a complex ballet of thousands of variables. Sometimes it feels like trying to herd a sack of fleas, blindfolded. Our traditional, often manual process were increasingly reaching their limits, illustrated by the $900 million irregularity cost of Lufthansa Group last year. My boss likes to tell the story from his long nights in the control centers of one of our subsidiary airlines before OPSD, where we tried to tame the chaos with paper lists, 1,000 phone calls, and way too much coffee. Sometimes he thought we need a magician rather than a manager. Previously, it was often an every man for himself approach. Now it's real teamwork, just with an artificial intelligence as an extremely capable and personal team member. The tail optimizer, it was the very first tool that we developed and put into production at Swiss back in 2021. The allocation of aircraft through specific rotations and its optimization is a well-known challenge within airlines. Yes, you can buy these tools on the market that do that for you, when you have the data and the necessary quality constantly available to feed an optimizer. And that's where the challenge begins for most airlines. And other than any other product out there, we added way more functionality to increase the levers and optimization goals from pure cost optimization with real-time revenue and cost elements, also to robustness of the schedule, for example, with crew connecting times. The tailsign optimizer is used daily, optimizing 90 short-haul and long-haul aircraft rotations at Swiss for the next 3 days to always consider the current plan and to also include reactionary measures by ops controllers. Until the end of 2025, we aim to have 400 additional aircrafts of the Lufthansa Group to be optimized in this way. We implemented a series of business IT and agility measurements to enhance operational efficiency and measure impactful results. One of the key innovations with the tail optimizer is offering cost transparency for operations for the very first time. Before that, decision makers and operations didn't know what every day or every flight costs us. Building up on this transparency, we were able to measure the impact of optimization and manual interactions of users with the flight plan on a daily basis. You can see with this dashboard the performance of the tail optimizer running in Swiss. In the first quarter of 2025, with $640,000 of savings, with more than 2,400 tons of CO2 savings, while changing almost 1/3 of already assigned aircrafts. However, other products out of the OPSD program need to be approximated by the number of data publications, usage rate, or saved resources to estimate their effectiveness and contribution to the organization because of the enormous complexity and dependency on multiple factors. With our recent development, the cancellation impact analyzer, we will elevate our steering approach from an aircraft-based to a truly passenger-oriented approach. We are now able to assess the impact of a cancellation on each individual passenger journey in terms of rebooking quality and costs before an actual decision. And this is at scale for hundreds of flights and up to 500,000 alternative passenger journeys per minute. So there was this case in Munich some weeks ago when one of our A350 had a hydraulic leak and the shift lead had 3 rotations to choose from to cancel. The difference between his gut feeling based on experience and our tool was a difference of $175,000 for one single long-haul cancellation. And we expect from this tool, which was introduced at Lufthansa and Swiss last month, double-digit million savings per year. And with the now available data transparency, we start changing roles, responsibilities, and processes in operation steering to reflect the new capabilities also in the organization. We need to establish roles that have the power to use these holistically data-driven results to execute it, which isn't possible with our current siloed environment. As previously mentioned, the overall impact of OPSD is truly remarkable. We are working with a team of 90 colleagues on this project, complemented by the Google research team. We have 2 airlines with Swiss and Lufthansa currently onboarded and aim for the go-live at Eurowings next month. We have achieved savings of more than $40 million and a reduction of 12,000 tons of CO2. That corresponds to about 600 flights between London and Zurich. When we first saw these CO2 numbers, it was a real goosebump moment. Knowing that our work directly contributes to more sustainable aviation is an incredible motivation. But it's not just about sustainability. What particularly pleases us is that we have been able to improve the passenger experience by optimizing control at our hubs and reducing misconnections. And our operations controllers trust these suggestions. The acceptance rate is on average above 90%. And this is actually one of the biggest challenges and will be in the future. The colleagues in operations control were trained and selected to take hundreds of small and big decisions every shift. So they tend to be more like James Bond, because not deciding would stop everything. With the increasing transparency because of more data, the adoption of AI and OR, there are new capabilities to allow for a better analysis of the impact of decisions before deciding. And to add to the complexity, the change within each airline of the Lufthansa Group is different, given the heterogeneous cultures and degrees of digital maturity of organizations and individuals. We are developing new solutions with the OPSD project for 4 years now, and we are far from done. We continue our feature development, especially based on the cancellation support tool, and extend our capabilities from single cancellation assessment to a scenario capability for summer 2026, and adding delay capabilities for 2027. Beyond that, we are currently evaluating future scaling to other Lufthansa Group airlines like Brussels, Austrian, and ITA. Inspired by OPSD, we extended the approach of augmenting existing legacy systems also to network planning to optimize schedules, not just for commercial purposes, but feedback operations insights. Once we have multiple airlines on board the OPSD platform, we can also tackle airline overarching optimization to further leverage the advantage of the Lufthansa Group. As a long-term vision, we believe that the aviation industry has a significant potential by sharing data in a more transparent way. Today, all players optimize for their own good, leading to conflicts and prioritization of scarce capacities. Aligning the interests in a better way, using data and technology in an industry cloud, will create benefits for all involved, especially for the customers of air traffic, and some bigger optimization problems to be solved by OR. The OPSD project is a shining example of cross-industry collaboration. It is a testament to our shared commitment to innovation, efficiency, and very importantly, a greener future of aviation. Many heartfelt thanks to the Edelman Award Committee for recognizing the importance of our work. We will continue to harness the power of data, applied analytics, to make the future of the Lufthansa Group and the entire aviation industry more sustainable and efficient. Thank you very much for your attention.